Then like to solve your problem and like double your work. I want to get this done, but I need to do it.
Okay, let's start. So I'd like to begin today's lecture. Do you remember the big picture we had in lecture number 2? So today is the second big picture of the course. And I calculated there are going to be 3.5 big pictures by the time we get to the midterm. So today is big picture number 2, which is the big picture of Gaussian naive Bayes. So this is another little picture that I think just kind of summarizes the situation on Gaussian naive Bayes in a kind of convenient way. It's easier to remember pictures for me than lots and lots of symbols. So I carry this picture around. So suppose we want to train a naive Bayes classifier. Let's take a very simple case. We have one continuous variable, x sub 1, and we're trying to predict a Boolean y. So maybe we're trying to predict whether a student is a basketball player, yes or no, and we'll use the height of the person as our single continuous variable. And so I might draw, here's my x1. That'll be height secretly. And my y's will be y equals 1 means you're a basketball player, y equals 0 means you're not. And so we already know all about naive Bayes, and so we know the decision rule shown here is that we're going to assign, once we train our classifier, and of course training the classifier just means that we use our training data to estimate two distributions, p of y, the prior that somebody's a basketball player, and p of x given y. The conditional probability on their height, given that they are a basketball player, that'll be one distribution we'll have to learn, plus another one for a condition on them not being a basketball player. And for the sake of this example, let's assume on average, although not completely every single time, but on average basketball players are a little taller than the normal student. So I might, in this case, say that, oh, here's a Gaussian distribution I could get that gives me, let's say, p of x given that y equals 1. Y is that, let's make that y equals 1. Y equals 1 distribution. And I can, of course, have another distribution for y equals 0. That'll be people who are a little bit shorter on average. Call that y equals 0 distribution. And in this particular case, I'm just going to make life very simple by assuming I have a sample of people I'm interested in, half of whom are basketball players. So the prior is just 0.5. They're equal. Okay. So now suppose I have a sample of people and I train. Of course, to estimate these, I just had to get the mu's and the sigmas, the means and the variances for those two conditional distributions. P of x given that y equals 1 and p of x given that y equals 0. And then if I have a new test example, a new x that I want to predict y for, I can just apply my decision rule up there. I'll assign the y that maximizes that quantity on the right just the product of the prior and the data, the probability of seeing the height. So, for example, if I see a new student over here, let's say this student, what would I predict? Y equals 1 or y equals 0? Of course, I'll predict y equals 0. The probability is higher if I multiply a probability of y equals 0 times its prior, 0.5. That's going to be greater than the probability of x given y times x given y equals 1 times 0.5. Yes?
It's a continuous xi. Why is it product of that is
The question is, why is it just the product and not the integral? The answer is, my new student has exactly this height, and so what I'm interested in is what's the probability that this person is a basketball player given that their height equals exactly 5 feet 10 inches. And so Bayes' rule tells us we just multiply the prior, 0.5, times, or our decision rule there tells us we multiply the prior times the conditional probabilities of those datas, of those observed x's given the y. So it's just what we've talked about. Okay? Yes?
It's a continuous distribution, so then you cannot assign x equal to something in the distribution. You only can define a range.
No, you guys are making this way more complicated than it really is. So I have a scale. The person stands on the, or I have a measuring stick. The person stands next to the measuring stick. I see they're 5 feet 10 inches. I write that down, and I just am trying to estimate the probability of y given that. And according to Bayes' rule, I just multiply these numbers. Okay. It's really no more complicated than that. Despite the fact that, of course, these are conditional distributions, or these are continuous distributions. I have a Gaussian distribution. There's some distribution of heights given that somebody is a basketball player that's, in this example, different than the distribution of heights given that they're not. That's reasonable. And because it's a continuous distribution, I might choose a Gaussian as a way to capture that. But when it grounds out in any given example, of course, there are no integrals or any fancy math involved. I just say, well, what's the probability of 5 feet 10 given that y equals 1? I put that into my Gaussian distribution. It gives me a probability density. And the same when I ask it for y equals 0. So it's really not complicated. It's really no different in style than when we had discrete variables, except the way we characterize the probability distribution here is in terms of a continuous Gaussian distribution. Everything else is the same. Pardon me?
It could be greater than 1.
The probability density can be greater than 1, but the integral under both of these two curves is 1. Okay, so really, this just applies, and if I were a careful mathematician following standard notation, I would have put little lowercase p's instead of uppercase p's there, just to indicate actually a lowercase p on the right hand on the conditional of x given y to indicate that that's a probability density, and I would have retained my uppercase p for p on y to indicate that that's a discrete distribution. But really, that's just mathematical detail that is inconsequential to us. Okay, so you can see the reason I drew this picture, this is part of the big picture, is because this picture makes it kind of glaringly obvious that I can easily summarize which x's, which new students, if the only thing I know about the new students is their height, which new students I'm going to classify basketball players, y equals 1, and which one I'm going to assign y equals 0. And you should be able to see that easily, right? For any given x, like this one, when I apply my decision rule up there, I'm just going to multiply two numbers and then compare them. I'm going to consider y equals 0 and y equals 1. And the two numbers I'm going to multiply, let's take y equals 1, is just the prior on y equals 1, which we agreed was going to be 0.5, times whatever the probability of that height given y equals 1. And then we'll compare that to the case where y equals 0. And so what that means is any point to the left of this threshold any point over here, it's more probable that y equals 0. Given x. Right? And any point over here, I'm going to label y equals 1. So this threshold is really my decision point along this axis. Right? And you can see it. The y equals 0 probability is higher than the y equals 1 if I go this side of the threshold, and vice versa if I go the other side. Yes?
Sure. This is a question, I guess, it's similar to that one. I guess given that it's continuous, can you say you can see that one is higher than the other? Or are you just reading the discrete, like at that point in the curve, or are you something?
Yeah, let's be precise. When I take this particular student, the comparison that I want to make is just this comparison. What's greater? This quantity when I plug in y equals 0, or this quantity when I plug in y equals 1? Okay, so to get this quantity, I have to multiply two numbers. One of them is this, which of course also equals y equals 0, the probability of y equals 0, because they have to sum to 1. So that number is going to be 0.5 in either case. And the only number that's really going to matter is the other one, which is this. And since I only have one feature, I'm not even taking a product there. It's just the one number. And so I'm just looking at, is this, there it is, p of y, this is p of x, given that y equals 1. And this is p of x, given that y equals 0, which is clearly higher. And therefore, I'm going to say more probable that y equals 0. Okay? So very straightforward. All right. Now, suppose I have another measurement. Another continuous measurement. X2. This will be their grade in the machine learning class. Another continuous variable, because we give real valued grades in machine learning. And unfortunately, because basketball players are on the road more, they get their homework in late sometimes. They don't study as hard as they should. Their grades in general, although not uniformly, are a little bit worse than people who are more attentive to the subject matter in the class. So I could have a second variable, x2. This is x1. Let's have another variable, x2. And again, I could draw a little curve of, now I'm going to need the conditional probability of machine learning grade, given that you're a basketball player and given that you're not. And so let's draw that here. Okay, so this is your machine learning grade. And here we have it for, these would be the non-basketball players, I'm guessing. And here we have it for basketball players. Right? And again, these curves that I'm drawing, this is literally the probability of x given y. One distribution for the probability of x given y equals 1 and one for y equals 0. And of course, if I used machine learning grade instead of height, you could tell me where the decision would be, right? Obviously, it would be right here. There's another threshold. if I don't know if I switch the problem around so the only single variable is machine learning grade, then obviously people who have grades above that are more likely to be non-basketball players, and people who are below that are more likely to be basketball players. Okay, good. So now, of course, in a real naive-Bayes classifier, we like to use more than one variable. Let's use them both. So what we're really interested in, and this is sort of Bayes' rule, tells us originally, the probability of y given x is just proportional to the prior on y times the probability of x, let's call that x1 and x2, given y. And of course, our naive Bayes conditional independence assumption says that we can re-express this quantity as the product of those different ones. Right? Okay, so now let's think about let's draw this on our plot. Okay, so what's going to happen is P of x1, x2 given y is really the product of these distributions that I've drawn along the single axes, right? Right. So for y equals 1, for example, the mean of my distribution is going to be here, an unfortunate location on the plot. But for y equals 0, it'll be up here. The maximum probability that I can get for, given that y equals 0, the maximum probability I can get for x1 and x2 is if I pick this point and this point right here. Right? And now I'll have a Gaussian distribution that looks kind of like that. Right? So this is now a terrain map of my Gaussian, two-dimensional Gaussian distribution. Right? Obviously, it's maximum where both of these are maximum because my conditional independence assumption says all I have to do to get the joint distribution on x1, x2 is multiply those. And similarly, so this is going to be, this distribution here is really my estimate of the probability of x1, x2 given that y equals 0. Right? And then similarly, there will be another terrain map here. I should have drawn it in another color to take full advantage of the technology, but you get the idea. And now you can see that in this two-dimensional space, I could take any x, a person of any height and any machine learning grade, I could plot them there, and I could see the probability of them occurring as an x1, x2, given that they are a basketball player and given that they're not. And just like I could make a decision point in the case that I used only one feature, now I can make a decision surface that separates out the points x that I would label basketball players from the points x that I would label not. Okay. And so now, let's say for the sake of argument, just to make life simple, let's assume in all these Gaussian distributions that I have, the probability of xi given that y equals k follows a normal distribution, a Gaussian distribution with some mean. There it is. Or these are the means along each of the dimensions. That's going to depend on the feature I and, of course, also the value y. And let's assume that it also follows some variance that is going to be the same for both of them. Makes thinking about these easier because now my terrain map surfaces are really circles. It's just a spherical two-dimensional Gaussian distribution. And in that case, it turns out the decision surface, so I guess it's time to change ink color. Then the decision surface is just going to be some straight line. On one side of this line, it's more probable that we'll observe the x's given the assumption that y equals 0. And on the other side of the line, it'll be more likely that we observe the x's given that y equals 1. Because of the height of the two terrain maps actually become equal in a surface that ends up being a line if we make this assumption. So this is a useful big picture, and if you really understand it, then you've got your head around the basics of our naive Bayes classifier. In fact, this is even true even if I assume that even if I allow the variance to change with the feature, but not the y value. So this is even true if I say, well, there will be a variance here that will be the same whether height is, whether y equals 1 or 0, the variance on height will be the same. If, and it will be the same if the grade variance will be the same for basketball players as non. And they don't have to be, the variance for height doesn't have to be the variance for machine learning grade. Then it will still end up being a linear surface. Okay. So this is the big picture that's helpful. Okay, now there's one more aspect of this. A question I want to ask you to test your understanding. Given that we all understand that big picture, now you should be able to answer the question, well, if we have the best case scenario, what is the minimum error that a perfectly trained naive Bayes classifier can make? So what's the best case? The best case is going to be if the conditional independence assumption of naive Bayes is truly satisfied, and we have, let's say, infinite training data, so we can perfectly estimate P of y and P of x given y. Or somebody just tells us what these distributions are. We're omniscient. We know P of y and we know P of x, either because we have infinite data or somebody let us in on the answer. Okay. So then, what's the minimum error I can get? Let's draw that picture again. Let's go back to just the single dimension. Here's again my two cases. This will be my just x1. And of course, here is P of x1 given that y equals 1, and P of x1 given that y equals 0. And let's say here's my decision threshold again. Let's call that point T for threshold. Okay, and these we've trained, we've got infinite training data, so we've estimated these two curves. And initially, let's just even assume we know P of y is just 0.5, so just to keep our thinking simple. Now we get a new student to classify. What's the probability that we'll misclassify that new student?
Small area engine.
Right, right. It's the probability that it's the probability under this region. Right? That kind of makes sense. If you think it through, what it really is the probability of an error is just the sum of two things. It's the probability that we predict let me do this in a way that makes my notation work out nicely. It's the probability that we predict y equals 0, but it's 1, plus the probability that we predict y equals 1, but it's 0. Okay, so now, what is this probability? Well, to put it in our notation, predict y equals 0, we could summarize that. We could equally say x is less than our threshold. So it's the probability that x is less than the threshold and y equals 0. And what's that? Now we can bring in our integrals, right? That is just this area. For every x that's in here, we're obviously going to want to predict y equals 0, because it's more probable that an x over here, a person of this height, is probably not a basketball player. That's more likely than them being a basketball player. But there will be a certain number of short basketball players, and they're going to be misclassified. And we don't want to change our strategy just for those people, because there are more non-basketball players below that threshold height. So we still need to guess that probably people below height t are non-basketball players. But we're going to suffer some unavoidable error from our optimal classifier when we do that. And that error, this probability, is just the integral from minus infinity up to our threshold. It's just this area. It's the integral from minus infinity up to our threshold of this. P of x given y equals 1, right? Y equals 1, not y equals 0. Right? It's the probability that we predict y equals 0 and y actually equals 1. So it's actually a joint probability. Oops. Oh, I see. I'm sorry. You should have corrected me at this point. Thank you. Those of you who attempted to correct me, but as my sister would say, I didn't have my listening ears on. She teaches kindergarten. There's the joint probability, right? And how come I can write this thing as this product? Chain rule, right? This is just the chain rule expansion of this joint probability. Probability of two things is just the probability of the first thing conditioned on the second times the probability of the second. Okay, so this is literally the probability of that event occurring. And then I have to add together that with this other possibility, which is what? That's the integral from what to what? Right, t to plus infinity of, well, now I want this density, the probability the x1 will be above that threshold. That's why I'm only considering this part of the integral. Given that y equals 0 times the probability that y actually equals 0. There it is. So you've just written an expression for the optimal error achievable in a world where the naive Bayes assumptions are really satisfied and we have enough training data that we're able to get perfect estimates of the parameters that we need for our classifier. That's pretty cool, right? So this is the best you can ever hope to do if this is the only variable that you have available to predict which students are basketball players, and if, in fact, basketball players really do, these conditional distributions really do follow Gaussian form. Okay, and obviously we could have written the same thing if we had x1 and x2 you could probably work out another integral if you had x1 through xn. In fact, then it would just be, instead of this simple line kind of scenario, it would be back to this. And we'd be looking at areas, well, you know, here's the region where we're going to predict y equals 1. How much probability mass from p of x given y equals 0 lies on the unfortunate side of that decision surface? That's going to be the probability mass associated with our, that characterizes the error we're going to get. Okay? So it's interesting. In these probabilistic models, it's not necessarily the case that we can always, even with infinite training data, get down to a training error or to a test error of 0. In fact, we may not even be able to get to a training error of 0. But what we're trying to do is just deal with a world in which that's the case. You know, if I ask you which is the person to your left or your right a basketball player, and you don't get to ask them, you won't be perfect, but you'll be better than random. And so that's the kind of world we're in. It's this kind of uncertain. We have a lot of probabilistic clues, and we want to combine them in an optimal way. And that's what this big picture kind of summarizes. Okay. So any comments, questions on that before we move on to logistic regression? All right. So logistic regression is motivated by a very simple observation, which is this. If what we're interested in is p of y given x, why on earth are we doing these contortions to instead learn p of y and p of x given y? Why don't we just learn p of y given x? And we started out, when we started looking at naive Bayes, saying, well, we're afraid to do that because the joint distribution, if we don't start making assumptions, could have too many parameters. But then we made this assumption, this conditional independence assumption, which wonderfully reduced the number of parameters we needed to estimate from exponential in n to linear in n. So it's a very constraining assumption, that conditional independence assumption. So why don't we now, armed with that assumption, go back and say, okay, if we make this conditional independence assumption, what would be the functional form, what would be the parametric form of p of y given x? And then let's just learn that form of p of y given x. So it'll be more restricted than if we don't make it. But let's see what form we would get if we start with our conditional independence assumption and ask what will p of y given x look like. Okay. So to be a little bit more precise, we're interested in learning a function from x to y, or equivalently p of y given x. X is a vector of real valued features, so we'll go with a Gaussian naive Bayes kind of formulation. Y is Boolean. We'll assume all the xi are conditionally independent given y. And we'll assume this is a Gaussian, we'll make the Gaussian naive Bayes assumption. And assume y is Boolean, Bernoulli, therefore. And notice here I'm making one tiny little additional assumption. I'm saying that sigma, the variance here, depends on only the feature, which feature it is. It can vary by feature, but it's not dependent on the value of y. So I'm not allowing it to vary by both the feature and the value of y. Same assumption we made when we were doing our big picture and looking at that linear decision surface. Okay, and here's the answer. Interestingly, if you ask under those assumptions, if I ask what's the form of p of y given x, the answer is it's this form, where my parameters, I could have written those w's as thetas to be consistent with our earlier notation, but these are the parameters that we have to estimate. from the training data. Okay? All right, now you might look at that and say, well, why is that the case? And here's the answer. So let's derive it. It's not that hard to derive. Okay, so as in so many cases, when we want to derive things, we start with Bayes' rule in this case. So I'm interested in getting the probability of y given x. And so I'll start with Bayes' rule. And just to make my notation a little easier, let's just consider first the case that y is, let's say, a Boolean variable. I'm just going to consider the probability that y equals 1. Of course, once I know that, 1 minus that will give me the probability that y equals 0. So I'm not degeneralizing at all when I do this. Okay, so there's just Bayes' rule. And then I can divide the numerator and the denominator by this numerator. Okay, so that makes my numerator 1, and now you can see it appears like this, right? And now, you know, what looks like a contortion, in general, the exponential of the logarithm of anything equals itself. And so I can substitute for this quantity the exponential of its logarithm. It looks kind of odd, but it's going to turn out nicely for us because in the final step here, what I'm doing is now I'm saying, well, the log of this product I can separate out as the log of this plus the log of this. Okay. So now what have I done? I've actually not yet made any assumptions about x or y being continuous or discrete. This is just Bayes' rule plus plus I made the conditional independence assumption when I went here. I went from the vector x to the x of i's. So I did bring in my conditional independence assumption here. But so far I haven't even said anything about, I haven't used my assumption yet that x is going to be continuous. But if I do, and furthermore Gaussian, if I bring in this assumption at this point, then I can just re-express this quantity in terms of a Gaussian. Oh, by the way, I should say that what are these pi's? I was just sticking with our earlier notation that pi was our estimate of the prior. So pi here is just our estimate that of p of y equals 1. Okay, so now if I bring in that exponential, or that Gaussian assumption, then this ratio, and you can work this out in detail yourselves. In fact, the required reading, which is on our website, goes through this in enough detail that you can follow the derivation pretty clearly. But it turns out that the sum over I of this logarithm, the logarithm of this ratio ends up being the sum over I of this quantity. And you see those mu's are the means and the sigmas are the variances of the two conditional Gaussian distributions p of x given y equals 0 and p of x given that y equals 1. So I'm not going to go through the tedium of deriving this here in class, but the wonderful thing is this is linear function of x. So when we put it all together, that's what we actually get. So when I showed you on the previous slide, this is actually the form of p of y given x, is this form. And you all gave me this puzzled look like, why on earth would that be? Now you see. It's precisely actually of this form. We even know what the parameter wi's are. If we train our Gaussian naive Bayes classifier and estimate our mu's and our sigmas, we can say, well, here's what the Wi will be, this quantity. And what will this W0 be? It'll just be the sum of those for all the xi's. Okay? So the point is it's a linear function of x. And the parameters that we're estimating from Gaussian naive Bayes, we can translate into the parameters that we want for W0 and W1. So one way to train logistic regression, if we believe these assumptions, the conditional independence assumption and the Gaussian conditional distribution assumption, one way to train logistic regression, which is essentially this form of a classifier, one way to train is to first just train our Gaussian naive Bayes classifier, get our estimates of the mu's and sigmas, use this formula to translate those into the parameters that we need for this form, and we're done. Turns out there's a better way in most cases where we're not sure about that assumption. There's a better way to train it, but this works if we're sure about those assumptions. Okay, so let's move on and look at the consequences of this. The beautiful thing about this is it's going to make our life wonderful, basically because this is now a linear function that we're dealing with. So we just derived the quantity for the probability that y would be 1 given the x's. What's the probability? Give me the form for the probability that y equals 0. It's 1 minus that, right? So 1 minus that would look like what? Well, let's give it the same denominator. And now what numerator do we want to give it? Right. If I give it this numerator, then obviously when I sum together this quantity plus this quantity, I get 1, which is what I need. Okay. So now we know both p of y equals 1 given x and p of y equals 0 given x. What's the ratio of those two? Right, just this. And what's the log of that? Well, that's just, we get rid of our exp. Now you see just how beautiful this is. Because remember last time in class we were talking about one way to do the decision rule, given any x, and we want to know whether to label it a y equals 0 or y equals 1, we agreed we could look at this ratio and just see if that ratio is greater than 1. Or equivalently, whether its log was greater than or equal to 0. And so our decision rule for logistic regression is just whether this quantity is greater than or equal to 0. And that is equivalent to asking, is it more probable that y equals 0 given x or that y equals 1 given x? So this is really cool. What we've done is we found a set of assumptions where if we work through from the starting point of Bayes' rule plus those assumptions, we can figure out the probability that y equals 1 given x and y equals 0 given x. And we've seen that under those assumptions, an equivalent decision rule is this incredibly simpler test whether this linear expression in terms of the x's for the x sub i's turns out to be greater than or less than 0. And that decision will every time be exactly the same as if we went back to basics, started with Bayes' rule, calculated the probabilities, and did it. But this algorithm that uses this expression won't need to do all those calculations. If it knows the wi's, all it needs to do is add up the linear sum. but every time it'll make the same decision a lot faster than an algorithm that went through the basics starting from Bayes' rule. So we've kind of compiled out the consequences of Bayes' rule into this equivalent, easy-to-use expression. So that's why I'm so excited about logistic regression. Actually, it's not. It's one of the two reasons I'm very excited about logistic regression. The other is that, let me skip that. The other is that it turns out we will be able to use this logistic regression form even when the conditional independence assumptions aren't really satisfied, and it won't always perfectly characterize the Bayes optimal thing to do, but it will usually do better than naive Bayes, at least if we have a lot of data to train it. But we'll get to that. Let's start by looking at the form of that function. So here's our form again. It actually ends up looking like this. So this is a familiar logistic function. Some people call it a sigmoid function. But essentially, if I say this quantity is b, the linear sum that I'm using is b, then the probability of y equals 1 given b given x is of this form. Okay? So as this quantity becomes increasingly negative, notice minus b is what I'm plotting there, then as it becomes increasingly extreme, then my probability goes closer and closer to 0 or 1. If this quantity itself is 0, then p of y given x is 0.5. And that's just a consequence of those Gaussian naive Bayes assumptions we derive this from. Okay. Let's generalize this a little bit. We started out by saying y is Boolean, but just like when we trained our bag of words, no, that's not a good. Just like in the homework where you're going to train your bag of words classifier on 20 news groups instead of 2 news groups, we could have y take on any discrete number of values. And if we do, then what we end up is generalizing our expression a little bit. Now we have to have a different expression for each y that it can take on. Suppose it can take on values from y sub 1 up to y sub r. Then for all but one of them, it's the topmost expression. And for the last one, because all these probabilities must sum to 1, it looks different for the last one. And again, it's easy to see that if we were to add to, both of these expressions have the same numerator. And for any given x, y must be one of its values, either y sub 1 or y sub 2 or y sub r or something in between. And so if you add together all the numerators for all the possible values of y, again, you get the denominator. So you can see it's really the same thing we were doing for 2 possible y's. We've just extended it to k possibles. By the way, it's a good thing to do. This is a good shower thing because you can use the steam on your shower screen to do it. Go back to our big picture and redo that big picture for the case that there are 3 possible values of y instead of 2. And see what those decision surfaces look like. Okay. All right, so logistic regression is that simple. And again, the key point is what we've done is we said, well, what if we make this conditional independence assumption plus the variance doesn't really depend on the value of y assumption, and then go from our Gaussian naive Bayes classifier to solve for what would be the form of p of y given x. Then we get this logistic regression form. So now, we already said one way to train that, of course, is to go ahead and train our Gaussian naive Bayes and then just use the arithmetic to convert those u's and sigmas into the equivalent w sub i's here. But we can also train it directly. In fact, this is the second reason why I like logistic regression. So we don't actually have to go through that intermediate stuff. We could train it directly. Now, how would we? So suppose we have some training examples, XY pairs again, just like always. We have L of those training example XY pairs. And now we want to train our logistic regression classifier. What does that mean? It means we want to estimate those W parameters from the training data to, in some sense, best fit the training data. Okay. You already know the story. Whenever we're in this situation, the two questions we ask ourselves are, well, maybe we could use maximum likelihood to derive an estimate, a method to estimate those parameters. Or maybe we could use map estimates instead, where we put a prior together with the data likelihood. And just like when we started there when we were estimating the naive Bayes parameters, we can start there again to ask, how could we derive a training rule for estimating these W's from the data? Okay, and if we did that, we have this set of training examples, 1 through L. If we wanted to get a maximum likelihood estimate, then of course what we're interested in is the set of parameters that maximize the probability of the observed data given the parameters that we choose. Right? Same as when we're trying to pick the parameter theta for the coin flip or the dice roll. Maximum likelihood we could do. And if we assume each of these training examples is independent, then that's just the product of the individual probabilities of each training example given our parameters. Now, we could do that, but in fact, here's a better thing to do in some sense. We don't really need to do that. When we apply our classifier, we already know X. So all we really need to do is worry about fitting our W's so that we predict the correct Y given X. So if you think about it, this is kind of a curious thing, but there's a sense in which naive Bayes, it learns two distributions, right? P of y, the prior is on y, plus, of course, P of x given y. And what that really means is it's essentially learning the joint distribution on x and y. Right? Because by the chain rule, if I multiply those two distributions together, that is P of x and y. It's the joint distribution on x and y. That's what naive Bayes. Once you've trained your naive Bayes classifier, you can multiply the two distributions. You've got the joint distribution on x, y. But like I said, we don't really care what P of x is. When it's classification time, somebody gives us an x. They give us a student. They say basketball player or not. We don't care what P of x is. We've got this student in front of us. We've got to classify them. So instead of this maximizing the likelihood of the XY pairs, what we could do is we could maximize instead the conditional likelihood of all the observed Y's given the observed X's that go with them and the W's. And by doing that, we're essentially picking the W's that are fitting just this conditional distribution y given x, which, of course, is the one we care about. And, in fact, this is the standard way of training logistic regression. So this is a kind of interesting difference between training naive Bayes and training logistic regression. Right? When it's naive Bayes, we're learning these two distributions, which is equivalent to learning the joint distribution the probability of P of X and Y. And here now we're going to be interested in P of Y given X. And so we can train just to maximize the conditional likelihood of the observed Y values given the observed X values. Okay. So this just says what I said in a easier to read font. So now we're going to talk about not maximum likelihood estimates, but maximum conditional likelihood estimate, which is just the parameters that maximize this conditional likelihood, conditional distribution on Y given X. And again, this product over L, that's each L here is just a different training example. So this is the product over every training example of the probability that we actually would have observed that Y given the X's that we observe and the W that we choose. And that's why we want to choose the W that makes it most probable. So it's the same story as maximum likelihood estimation, except we realize the thing we really care about is just the conditional distribution, and therefore we'll use the conditional likelihood. All right. So now some math. And again, in this case, I'm going to go through this quickly, and I encourage you to take a look at the reading and kind of redo the math in your own time. But I don't want to go through the tedium of that here. But let's just glance at it, because it's actually very straightforward, freshman calculus kind of stuff. I'm going to talk about the log of the conditional likelihood. So here's our conditional likelihood again. And my job now is, given a set of training data, a bunch of X, Y pairs indexed by L, I want to choose the W that maximizes that quantity I just drew a red box around. Equivalently, I could maximize the log of the quantity. That doesn't matter. Log is easier to work with, as it often is. So I'll do that. And again, I'll do it under this assumed form for the logistic function, the form that we just derived a moment ago. And so if I just do substitutions here and multiply things out, essentially, let's look at this first expression because it's very straightforward. If I want the sum over all examples, this is the ELF training example, of its conditional likelihood, the probability of its observed Y given its observed X, and some W. Well, in the case where Y equals 1, that's going to be this quantity. In the case where Y equals 0, it's, of course, going to be this quantity. In the case where Y equals 1, it's just the log of the probability that Y equals 1 given X. In the case where Y equals 0, it's going to be this. And this is just our old trick for how to write an if statement as a linear equation. Right? Notice if Y equals 1, the left term will be selected and the right term will be zeroed out. If Y equals 0, the left term will be zeroed out, the right term will be 1. So it's just an if statement. But now, starting with that, I can then do some manipulations. The first manipulation is to expand this thing on the right to the 1 minus Y. I'll multiply by that and do some subtracting and noticing that the log, if I subtract the log, it's like taking the log of the ratio. So that gets me here. And now this ratio is actually what we asked on slide number N earlier, and you told me the ratio was just this quantity, which it is. And this quantity is just the probability that Y equals 0 given X. And notice I've put a minus sign here because, remember, it was that probability is 1 over this quantity, so minus the log. Okay, so it's just straightforward freshman calculus kind of manipulations. But this gives me a form for the log of the conditional likelihood of my training data for any W, set of W parameters that I happen to plug in. And now I want to optimize that. I want to maximize, I want to choose the W's that maximize the conditional likelihood of my observed training data. And I've got, again, an optimization problem. And how did we solve it before? We took the derivative and set it to 0. We can take the derivative of this, but sadly, it's not a convex function. So just setting it to 0 is not quite going to solve our problem. Instead, we're going to have to do a more tedious optimization method called gradient ascent. But again, it's based on calculating the derivative of this and using the derivative of this to find the optimum values of W that will optimize it. I'm sure many of you have seen gradient descent before, but let's take a quick look at it and see how we would solve this. So, oops. So let's look at how we would solve it. Actually, this doesn't qualify as one of the 3.5 big pictures that I was talking about before in the midterm. But if you don't already have this picture in your head, you should put it in there. It's a very valuable picture. This is a picture that characterizes gradient descent. So in this case, suppose I have, so in our case, we're interested in using gradient ascent to find the W values, our parameters W, that will make the conditional likelihood of our training data the highest it can be. So we've got an optimization problem. We've got some function, in our case, the conditional log likelihood. We're trying to find the values of W that will make that function value as high as possible. Okay, that would be gradient ascent. Here I've drawn gradient descent, so you can just flip it over and you'll have gradient ascent. But the picture is very simple. Here in this plot, I have two parameters, W1 and W0, which can vary, continuous parameters. Just like in our logistic regression function, we're trying to pick W's. And if I could afford it, which I can't, I could actually plot the value of my function that I'm trying to optimize at every given W1, W2 point. For every possible value of W1 and W0, I could plot the value of that function. In our case, that would correspond to training a logistic regression function with just these W0, W1. And our surface here with the function we're trying to optimize is the data likelihood, the conditional data likelihood. And of course, we get a different value depending on which W's we pick. It'll turn out to be a smooth surface. As we vary W sub I just a little bit, it'll change the function just a little bit. And so gradient descent is a way of finding the optimum. In this case, we're trying to find the minimum instead of the max in this picture. But the procedure is very simple, which is we start with some random place. I see. We start with some random place. We calculate the derivative of our function we're trying to optimize with respect to W0 and W1 at that point. Of course, the derivative is going to be different depending on which W0, W1 we pick. We calculate the gradient at our starting random W's. And then we move the W's in the direction that takes them downhill the fastest. How do we know that? That's what the derivative is. In fact, the gradient is just the gradient, this is gradient, of the error function that we're trying to optimize here is just the vector of derivatives of that function with respect to each of our W's. So it's a vector of derivatives. And that gives us a direction. We move in that direction. We move each of our W's in the direction of the gradient. And now we get a new value and the new derivatives. We calculate those new derivatives, and then we take another step. And if we keep doing this, we'll keep going downhill until we get to the bottom of the thing. So it's an iterative procedure for hill climbing or hill descending, depending on whether you go up or down relative to the gradient. And if we have a function with a single optimum, then we're going to get to that optimum. Okay. I misspoke earlier. Some of you may have picked that up. When I suggested that logistic regression does not have a single optimum, in fact, it does. And you will get to it. But there's no closed form solution, so you have to use this gradient procedure to do it. Okay, so basically what that means is now we've got an algorithm that we can use to train our logistic function as long as we know the gradient of the log conditional likelihood of the training data with respect to each of those parameters w sub I. And that's shown here. And again, you can verify this at your leisure, that the derivative of that log likelihood is, in fact, this quantity.
As you commented earlier that the object function is not convex, so there might be several local optimal. But you then says for logistic regression there is only one, so we
Right.
always get to that.
So I think I misspoke when I said that there's only one optimum. If you do logistic regression, you get and you do this gradient procedure, you get the optimum. But there's no closed form solution for the maximum conditional likelihood estimate the way there was, say, we had a closed form solution for getting maximum likelihood estimates of our coin toss parameters. You know, we derived a closed form solution, which was just take the ratio of observed heads to all flips. We don't have a simple formula like that we can just plug in our data and calculate the optimum. Instead, we have to go through this gradient descent procedure to achieve it, but we will achieve it. And that's why I said a moment ago that, oh, I misspoke when I suggested that you wouldn't get to the optimum solution. You will, but you've got to go through this iterative procedure to get there.
All right, can I say that although it's not convex function, object function, but we theoretically prove that these logistical methods can go to the optimal in some sense?
Right. Let me just say there's a single global optimum, and we get to it by gradient descent. That's the only statement I really want to make at this point. Okay. Yes.
By this gradient descent iterative procedure, we get a set of values that may be different from what we might get from the naive base.
Naive base.
Yeah. So that is because we are having different object functions.
Now, that's a very good question. So in case you didn't hear that in the back, I'm going to repeat it. That's an excellent question. If we do this gradient descent, or in our case, gradient ascent, because we're trying to maximize the conditional likelihood, if we do this procedure, will we get to the same functional form as we would get if we trained our Gaussian naive Bayes classifier and then just did that translation of those mu's and sigmas into the w's? And the answer is not always, but I can guarantee it under some conditions. So here's the condition under which I can guarantee it. If I have infinite training data, so there's no variance that I have to worry about there. If I have infinite training data, so in other words, I have enough data to perfectly estimate the parameters, and my conditional independent, my Gaussian naive Bayes assumptions are all satisfied. Fundamentally, there are three of them. One, that the conditional distributions really are Gaussian. Second, the conditional independence assumption. And third, that assumption we brought in when we did the derivation of P of y given x, which was that the variances may depend on what the feature is. They might vary by feature, but they won't vary by y value. If we make those three assumptions and I have infinite training data, then I can guarantee that I'll get the same decision surface using this gradient method for deriving my W's as I would get if I instead trained my Gaussian naive Bayes, mu's, and sigmas, and then derive the W's from that expression we saw. Only in that condition do I think that I can guarantee that they'll be the same. And interestingly, you can translate from the Gaussian naive Bayes parameters to the logistic regression ones, but not vice versa. Do you see why? Why you can't go the other direction? You cannot go the other direction because Gaussian naive Bayes is learning the joint distribution. It's learning P of x and y. But logistic regression is only learning the conditional distribution, P of y given x. And so it doesn't have the full information about the joint distribution. But what it says about P of y given x will be exactly correct in that infinite data correct assumptions situation that I just mentioned. So that's a great question. If you really think that through and think about the consequences of not having infinite data and stuff like that, that's a good way to think about the relation between these two.
So the result is that if those assumptions do not hold, then the Gaussian naive Bayes is not optimal in the sense of conditional non-likelihood.
If you have infinite data and you learn P of the joint xy perfectly, then you can compile out of that the perfect answer to what is P of y given x.
But what if those conditional independent assumptions do not hold?
Oh, well, if the assumptions don't hold, then these two procedures will give you different answers.
Yeah, and in this sense, the naive Bayes will not be optimal.
If the naive Bayes assumptions don't hold, then naive Bayes will surely not be optimal. And let's come back to that. We're going to actually peel that apart and look in more detail at this correspondence between the two methods, because this really is one of the key points in the first half of the course, is that what we've done here is we've identified basically two kind of complementary ways of training what might end up being the same classifier. You know, we started with naive Bayes, and then we derived the answer to the question, why don't we just learn some parametric form for P of y given x directly? What would that even look like? What would be the parameters? What would be the form? We derived that. We saw it was this logistic function form. Now we've got a training procedure for it, too, that's just different from naive Bayes. But we know, under the assumptions that we made when we did that derivation, that there's a sense in which these are, I won't use the word equivalent because they're not. One of them is learning just the conditional distribution of y given x. In fact, people call that a discriminative classifier because P of y given x just discriminates the x's for which y equals 1 from those for which it's 0, but it doesn't capture the full joint distribution, P of x given y, which of course we could calculate from the two probability terms that we get from naive Bayes, P of x and P of x given y. Sorry, P of y and P of x given y are the two we get for naive Bayes. So this idea that that we can learn was called a discriminative classifier. In fact, people call naive Bayes a generative classifier for reasons that we'll discuss soon. This idea of there being these kind of pairs of ways of doing things is something that we'll come back to a couple times in the course. And this is the first example of it that we're seeing. And so it's interesting to tease apart, you know, when would you want, so now you should be asking yourself, gee, when should I use naive Bayes? When should I use logistic regression? If you have infinite data and the assumptions of naive Bayes are satisfied, it really doesn't matter, except that it'll probably be faster to train naive Bayes than it will logistic regression, because we do have closed form solutions to their maximum likelihood estimates, whereas we have to do this iterative training of logistic regression. But since we're usually not in the infinite data case, you should be asking yourself, well, how do I decide which of these methods to use when? So let's begin down that road. So here, and again, this is all covered in the reading, so you can go through this in more detail. But once you go through all the math to derive this gradient update rule, it actually boils out to a very simple rule, which is we're going to take our training data, and then we're going to make up some random starting values for W, for all of our W's. Many people like to use 0 as a good initial point for their W's, although you don't need to. And then what we're going to do is iteratively take gradient ascent steps, each time increasing, picking new values of W's that will increase the conditional data likelihood until we notice that we've maxed out. And on each of those steps, here's the rule for doing it. It just says replace W sub I by its new value, which is its old value, plus this change. And let's look inside and see what that is. It's actually very intuitive. What is this saying? Remember, y is a Boolean variable, can be 1 or 0. So let's suppose, and L again is the superscript for the ELF training example. And so what this rule is saying is change W in proportion to the difference between the observed value of y on this ELF training example and the value of the probability that you would predict that its value is 1 given x and the w's that you have at the moment. So think about that. Suppose the true value is, let's say, 1. And we predict that y equals 1. And we predict it with probability 0.9 that y equals 1. Then this will be 1 minus 0.9, 0.1, a kind of a small amount. On the other hand, if we predict we really don't know if probability of y equals 1 is 0.5, then this will be a larger term, and we're going to make a bigger change to wi. If this is 0, if we predict that this is a 1 and we predict this is 1 with probability 1, then there will be a 0 term here. We won't make any change to our w's. We're there. On the other hand, if y equals 0, this works too, right? If y equals 0, we want the probability that y equals 0 to be 1, which is equal to saying we want the probability of 1, y equals 1, to be 0. So if y equals 0, we want this probability to be 0, meaning that it's not 1, it's 0. And 1 minus this quantity is the probability that it's 0. So basically, this quantity is saying, look at the difference between the 0, 1 label and the probability that you're assigning the correct label, and try to make the probability that you're assigning the correct label equal 1. And if it's not, then make a change to w in proportion to how far off you are. And also how big x sub I is. But that's what the gradient rule is doing. So intuitively, it kind of makes sense. But that follows directly from just the standard calculus that we're using to derive it. It's easy to extend this to, instead of maximum conditional likelihood, to say maximum conditional a posteriori estimates of the w's. You can guess how to do this. It means just as before, we want to put a prior on our w's. And the standard way of doing that is to, a very common way is to say we're going to put a prior on our weights that we think they should be close to 0. How can we do that? The simple way to do that is to put a Gaussian prior on every weight who's centered at 0. The mean of the Gaussian is 0, and then some variance around it. And so then that's a way of encouraging our weights to be 0 unless the training data suggests they should be otherwise. So think about that, and we'll pick it up there next time. Good. Thanks.
I just wanted to say that they say